Hi everyone, welcome to lecture 28 of your electric circuit class, and the lecture is about Thevenin and Norton's theorems. The objectives of this lecture is to use Thevenin's theorem to find voltages and currents in AC circuits. And the second objective is to use Norton's theorem to find voltages and currents in AC circuits. So we'll start with Thevenin theorem. And Thevenin theorems states that any linear circuit across any two terminals can be presented by a single voltage source, which is called Thevenin voltage, and that should be connected in series with an impedance, and that impedance is called Thevenin impedance. To illustrate this, if we have a linear circuit and it has two terminals, let's say A and B, we can represent this as a voltage source called V Thevenin, and that is of course a phasor quantity, and connected in series with an impedance called Z Thevenin, and this is our terminal here, AB. Which means, for example, that if I have a circuit, and that circuit, it has, let's say, a voltage source, it has a resistance, an inductance over here, it has a resistance, a capacitance over here, and then another resistance and capacitance, and over here, let's say, we have an inductance, and we are saying that find V naught. So in this case, since the question is asking us to find V naught, then we have to open this element. So to open this element, we do this, so that is open, and now I have a terminal over here. So that terminal is terminal AB. Then for this circuit, I can come up with a voltage source that is called V Thevenin. Then we have an impedance here called Z Thevenin. And this is where our Thevenin equivalent circuit. Then the question was to find V naught, then we will put that inductance back and we will find V naught over here. So, regarding Thevenin theorem, these are the steps. Let's say that if the circuit has only impedances and independent sources, so the steps that first we need to find V Thevenin and V open circuit, and that is of course at the opening. This is where we need to find V Thevenin, at the opening. And then after that, since the circuit it has only impedances and independent sources, then we can turn off all sources and then find Z Thevenin across the opening. So we will find Z Thevenin exactly at this location as well. The second method that we have to look at the circuit. If the circuit has impedances, has independent sources and dependent sources, so both sources are in the circuit, then the recommended method is to find your V Thevenin, which is V open circuit, that is across the opening. And then after that we need to short the opening. So this is the terminal over here. We have to short it and then find I short circuit. Then we have V Thevenin and we have I short circuit. Then we'll be able to find Z Thevenin. Okay, so we cannot, when we have this here, we cannot use the reduction method to find Z Thevenin. We have to find the I short circuit and the V Thevenin, and then we'll say Z Thevenin is equal V Thevenin over I short circuit. Sometimes that you have circuits that will have impedances and only dependent sources. In this case, since no independent source there is, that means there is nothing is deriving, let's say, currents to flow in the circuit or voltages to be dropped across any impedances, which means that it is right away that V Thevenin or V open circuit in this case is equal to 0 volt. And the second step to find Z Thevenin, what we need to do, we will just connect across the opening and open a voltage source, and we will give it a value. Let's say that this is 1 volt. If we give that as 1 volt, then we have to find the current flowing through that, let's say, source, and then we will say Z Thevenin is equal to 1 over I source, the one that flowing through the source. This one here, because we have assumed that the voltage is 1 volt, which is 1 with angle 0. Of course that you can assume any value you want, because as you know that the current and the voltage are related through a linear relationship. The higher the voltage is, the higher the current. However, the ratio of voltage to current will remain the same, and that is how we can find, let's say, our Z Thevenin, regardless of the assumed value for the voltage source. So let us go over an example over here. And the example is asking us to determine I naught in the circuit using Thevenin's. And this is our circuit here. Six with angle 0 volt. This is J4 ohm. 3 with angle 0 ampere, and this over here the impedance is 2 minus J2 ohm. There is a current source here going downward, and the value of it is 2 with angle 0 ampere. There is an inductance here, it is J1 ohm, and the current that we need to find is this current here, which is I naught. So I naught is flowing through the J4 ohm resistor, inductor. Our solution here. So if we look at our methods over here and we look at the circuit has only impedances and independent sources, which means that we are going to go with method number 1. First, we need to find V Thevenin and then find Z Thevenin through the reduction method. And this is what we will do. So find V Thevenin. How to find V Thevenin? We need to draw our circuit. So This is 6 with angle 0, 2 with angle 0 ampere, 3 with angle 0 ampere, 2 minus J2 ohm, and this is J1. And if you look at this here, our requirement is to find I0, so we need to cut this element out. So this is what we will do. We'll cut the element out. Then this is where we need to find our VThevenin. If I put positive here and negative here. So now, to find that VThevenin, if I know the voltage at this node and the voltage at this node, then the difference between them, that will be our VThevenin. So we will assume this as V1, this as V2, and this node here as V3. And let's say our reference is here. So now we need to use nodal analysis. So at node 1, we can say that V1 is equal to 6 with angle 0. And this is our first equation. Why is that? Because there is only voltage source between this node and the reference. So that is a super node. So V1 minus 0 is equal to 6. It will end up with V1 is equal to 6. Now at node 2. At node 2, we can say V2 minus V3 divided by 2 minus J2, which is the current flow in here. Now we will go with this current, plus 2 with the angle 0 is equal to 0. So if you look at 2 minus J2 here in the denominator, so 1 divided by 2 minus J2, that will come out to be 0.25 plus J.25, and that is multiplied by V2, and then minus the same quantity, 0.25 plus J.25 V3, and that is equal to negative 2 with angle 0. And this is our second equation. At node 3, if you look at node 3 here, this is node 3. So we can write V3 minus V2 divided by 2 minus J2 plus 3 with angle 0 plus V3 over J1, that is equal to 0. So again, 1 divided by 2 minus J2, that will be 0.25 plus J.25. That is multiplied by V3 minus 0.25 plus J.25 times V2 minus, now 1 divided by J1, that will be negative J1, so negative J V3, and that is equal to, we bring this one to this side, and that will be negative 3 with angle 0. So let us now put that in order. We will have negative 0.25 plus J.25 V2, and then plus, now V3, I have this as V3 and over here is V3, so I have J.25 and I have minus J, so that will be 0.25 minus J.75 V3 is equal to negative 3 with angle 0, and this is our third equation. So now we put in matrix form. We are gonna get this arrangement here. That is 1, 0, 0, 0, 0.25 plus j 0.25, negative 0.25 plus j 0.25, then 0, negative 0.25 plus j 0.25, and then this positive 0.25 plus j, sorry, minus j 0.75, and that is multiplied by V1, V2, and V3, and that is equal to 6 minus 2 and minus 3. So when we solve this matrix, we are gonna get our V1 to be 6 volts, our V2 to be negative 4 minus J1 volt, and our V3 to be negative J5 volt. However, we are looking for V Thevenin is equal to V1 minus V2, and that is equal to 6 minus, and V2 is negative 4 minus J1, and that is equal to 10 plus J1 volt. However, that we need this in polar form, so we will convert from rectangular to polar, and that will be 10.05 with an angle of 5.71 degrees volts. So this is our Thevenin. The second step is to find Thevenin. So now, as I said, that we look at the circuit, it has only independent sources, no dependent sources in the circuit, then we can go with the reduction method. So to go with the reduction method, we need to turn off the sources, and this is where our terminal at, so we need to find Thevenin here, and that is a voltage source. We will short it. So this is 2 minus J2, and that is J1. So if you look at this here, for our Thevenin, it is really, you can, let's say, assign nodes if you want to be able to draw it. But however, if I have a current injected here, then this current is gonna flow this way, go back this way, and go back to the other side of the terminal. That means all of these elements are in series. So our Thevenin is equal to 2 minus J2 plus J1, which means that is 2 minus J1 ohm. And this is our Thevenin. If you don't want, if you cannot determine that, then the best way is to assign nodes. So this is node A, this is node A, this over here is node A, this is B, that means this is node B, right? So now if you look at that, I can put A here, and we can put B here. So between A and B, we have all of these elements in series. So that will be the resistance, the capacitance, and the inductance in series. So 2 minus J2 and J1. Then that will give us that Z Thevenin to be 2 minus J1 ohm. So now we will draw our circuit, which is the Thevenin equivalent. That is a plus minus. Our V Thevenin came out to be 10.05 with angle 5.71 degrees. That is in volts. Then we have our Thevenin impedance. Since that it came out to be 2 minus J1, that means this element here is a capacitance. So that is 2 minus J1. So this is our Thevenin equivalent circuit. However, we are looking for I naught, the one that flowing through the J4 ohm reactance. So we will put that inductor back. And this is where we need to find I naught. And the value here is J4. That means our I naught is equal to 10 with 10.05 with angle 5.71 degrees divided by the total impedance, since we have a single loop here. So that will be 2 minus J1 plus J4. And that is equal to 10.05 with angle 5.71 degrees divided by 2 plus J3. And the answer here is 1.77 minus J 2.15 ampere. However, since it is a current, we would like that to be in polar form. And that is 2.78 with an angle of negative 50.6 degrees. So this is our answer for I naught using Thevenin equivalent circuit. So now, regarding the Norton, again, if we do have a linear circuit with two terminals, then this circuit can be presented as a current source in parallel with an impedance. The impedance called Zn, which is Norton impedance, and the current is called In, which is the Norton current. So they are connected in parallel. So it is the same thing that if I have, let's say, a circuit over here, and that circuit, it has, let's say, a voltage source, an impedance over here, an impedance over here, another impedance over here, another impedance over here, and we would like to find, let's say, V naught here. Then what we have to do, we have to make this circuit, this here, it will represent our linear circuit. Then we will have this point and this point as the terminal, because this here we need to cut it. So cut this out. So if that is element 1 here, we will cut element 1 out. Then we will have our Norton equivalent circuit will be like this. Because we cut this out. Then over here that we need to find our V naught. So we will just connect that back. And then we can find V naught over here after we found In and Zn. So regarding Norton theorem, these are the steps that you can follow. These are like recommended steps. So the first method that you look at the circuit, if you have only impedances and only independent sources, then you can short the terminals. So when we have the terminals like this, we short that and we find I short circuit. This I short circuit is equal to Norton current. Then the second step is to find your Z Thevenin. So Z Thevenin across the opening, you need to find, this is ZN, which is Norton equivalent, which is equal to Z Thevenin. Okay, so you will find Zn here, which is the same as Z Thevenin. Then the second method that under the condition we have impedances and we have both the independent sources and dependent sources. So we need to find first the V Thevenin, which is the open circuit. That is the open circuit at that terminal. And then we need to find our I short circuit. So when we have the terminal, what we need to do, we will just short it and then find I short circuit. Then our Z Thevenin is equal to this V Thevenin over I short circuit. V Thevenin, we found it from the first step. I short circuit, we found it in the second step. And then we will substitute to find the Zn. So Z Thevenin here, that is the same as Zn. Same thing, okay? And then the third one, that if you have only dependent sources, then right away that our IN is equal to I short circuit, and that is 0 because there is no any independent source to drive voltages or currents. And then the second step is to apply a voltage source. So when we have the opening like this, the terminal, so we will just apply a voltage source and we will give it, let's say, a value of 1. Then find the current through it, which is IS. So in this case, to find Z Thevenin, we assume the value of the voltage source to be 1 volt. And then we found I short circuit based on that 1 volt. Of course, you can assume any value over here because the higher the value of the voltage, the higher the value of the current. So the relationship between voltage and current is maintained. The ratio is fixed. So let us go over an example over here. And in our example that we would like to determine Vx in the circuit, using Norton's. And our circuit look like this. This is 6 with angle 0. This is J6 ohm. This is 2 ohm resistance. This is 6 ohm resistance. This is 2 ohm. 2 ohm. This is J6 ohm. We have a capacitance over here, and that is negative J1. And then we have a dependent source, which is a voltage source, and that is 2Ix. And our Ix is the current flowing here. And our Vx that we need to find is this Vx here. So that Vx is this Vx here. So this is what we need to do. So now, our solution, if you look at the steps in the table, you look here. So this is method number 2 because we have impedances, we have independent sources, and we have dependent sources. So the first step is to find V Thevenin, which is V open circuit. So this is what we will do. Find V open circuit, which is V Thevenin. where across the opening. Where is the opening? We will open this element because this is what we need to find. So our circuit will look like this: negative, positive, 6 with angle 0, J6, plus minus 2ix minus J1, J6, this is Ix, that is 2 ohm, this is 2, and this is where we need to find V open circuit, and this is 2 ohm. So V open circuit, if our, let's say, ground is here, then this here is V open circuit, that is, let's say, V1, and this is another node, V2. So we will write our equations. At node 1, at node 1, that will be V1 minus 6 with angle 0 divided by J6 plus V1 minus V2 divided by 2, that is equal to 0. So now 1 divided by J6, right? We can do, we will repeat because over here I forget this 2 here. So that is V1 minus 6 with angle 0 divided by 2 plus J6 plus V1 minus V2 over 2 is equal to 0. So 1 divided by 2 plus J6, that will give us 0.05 minus J.15 multiplied by V1 minus 0.3 minus J.9 plus 0.5 V1 minus 0.5 V2 is equal to 0. So now collect the terms. That will be 0.55 minus J.15 V1 minus 0.5 V2, that is equal to 0.3 minus J.9. So here that is negative or minus the whole quantity, 0.3 minus J.9. So when we bring it to the other side, it will become positive 0.3, and it was positive 0.9, then it became negative 0.9. And this is our first equation. Now at node 2. At node 2, we have V2 minus V1 divided by 2 plus V2 divided by J6 plus V2 minus 2Ix divided by negative J1, that is equal to 0. So we will simplify. V2 divided by 2, that is 0.5 V2 minus 0.5 V1 minus J. So the J over here, we brought it up to the numerator, became negative J, and 1 divided by 6, that is 0.167 multiplied by V2. And then now I have negative J1. When I bring it up there, it will become positive J, and then 1 divided by 1 is 1. So that will be plus J V2 and then minus J2 Ix is equal to 0. So now we will collect the terms. We will have negative 0.5 V1 plus 0.5 plus J 0.833 times V2 minus J2 Ix is equal to 0. And this is our second equation. So we have two equations, however we have three unknowns, V1, V2 and Ix. Then we need an equation for the controlling variable Ix. Our Ix is equal to V2 divided by J6. And from that we can say V2 minus J6 Ix is equal to 0. And this is our third equation. So now we can put these equations in matrix form, and that is 0.55 minus J 0.15, negative 0.5 and 0, then negative 0.5, 0.5 plus J 0.833 and 1, 0, negative J2 and negative J6. Those are multiplied by V1, V2 and Ix, and that is equal to 0.3 minus J 0.9, 0 and 0. And when we solve, we are going to get our V1 to be 0.088 minus J 1.853 volts, V2 negative 1.059 minus J 0.264 volts, and Ix came out to be negative 0.044 plus J 0.176 ampere. So from that we need our V open circuit, and V open circuit in this circuit, that is equal to V1, which is equal to 0.088 minus J 1.853 volts. However, that is our what? That is our V open circuit. So now the second step is to find Z Thevenin. How to find Z Thevenin? We need to look at the circuit. The circuit has both dependent sources and independent sources. That means we have to find I short circuit. So in this case, our circuit will look like this. This is 6 with angle 0. There is an inductance here, and that is J6, 2 ohm. That is 2 ohm. Now this is where the terminal was, so we will short it, and then we will find I short circuit. So this is 2 ohm, J6, and then we will have our capacitor here and the dependent source over here, plus minus 2Ix. This is minus J1, that is J6, and the current is flowing here, Ix. So we need to find our I short circuit. So if we go with I1, I2, and I3. So these are the loop currents. So we will start with loop 1. For loop 1, we can say 2 plus J6 I1 minus 6 with angle 0 plus 2 times I1 minus I2, that is equal to 0. Then we will end up with 4 plus J6 I1 minus 2 I2 is equal to 6 with angle 0. And this is our first equation. So now we will go with loop 2. Excuse me. Loop 2, that is 2 times I2 minus I1 plus 2 I2 plus J6 I2 minus I3 is equal to 0. Now collect terms. We will get negative 2 I1 plus 4 plus J6 I2 minus J6 I3 is equal to 0. And this is our second equation. Now we go with loop 3. Loop 3, that is J6 I3 minus I2 minus J1 I3 plus 2IX is equal to 0. So now we collect the terms for this equation. So that is negative J6 I2 plus J5 I3 plus 2IX is equal to 0. And this is our third equation. Now we have 3 equations, but we have 4 unknowns. Then we need to find the controlling variable equation, that is Ix. Our Ix with respect to the loop currents, that is equal to I2 minus I3. So from this, we can write I2 minus I3, and bring that Ix to the other side, that is minus Ix is equal to 0. And this is our fourth equation. So now what we need to do, we'll just put that in matrix form. And when we put that in matrix form, it will look like this. 4 plus J6 minus 2, 0 and 0, minus 2, 4 plus J6 minus J6, 1, 0, minus J6, J5, negative 1, 0, 0, 2, and negative 1. And that is multiplied by I1, I2, I3, and Ix. And the right side of the equations, that is 6 with angle 0, and the rest are zeros. So now when we solve this, we are going to get our I1 is equal to 0.431 minus J 0.827 ampere. I2 came out to be 0.345 minus J 0.362 ampere. I3 came out to be 0.379 minus J 0.448 ampere. And our Ix came out to be negative 0.034 plus J 0.086 ampere. And what we are looking for is the I short circuit. I short circuit based on our orientation of the loop currents, that is I1 minus I2. So I1 is 0.431 minus J 0.827 minus I2, which is 0.345 minus J 0.362. And the answer here is 0.086 minus J 0.465. In polar form, this is equal to 0.473 with an angle of negative 79.51 degrees, and that is in ampere. So our Zn, that is equal to V open circuit over I short circuit, which is V Thevenin over I short circuit. V Thevenin came out to be 0.088 minus J 1.853 divided by 0.473 with angle negative 79.51. And the answer here is equal to 3.89 minus J 0.53 ohm. Usually when it comes to impedances, we like the final expression to be in rectangular form. The reason behind that, because we will be able to find the value of R and we will be able to find the value of our X. So now our circuit will look like this. So this here, the impedance, now we know it. And that is a resistance and a capacitance. This is our terminal. So this is here 0.473 with angle negative 79.51 degrees, and that is in ampere. And our Norton impedance, it is 3.89 and minus J 0.53. And then now we need to reconnect the resistance back, the one that we cut at the beginning, and that was 6 ohm. And this is where we need to find our Vx. So based on that, we can say our Vx, we can use current division. The current division over here, if you look at that, we do have the current flow in here, and there is a current flow in here. To find this current, if I call that as I1, let's say, then Vx is equal to I1 times 6. And I1 is 3.89 divided 3.89 minus J 0.53 divided by 3.89 minus J 0.53 plus 6. That is multiplied by 0.473 with angle negative 79.51. That is what this over here, the whole thing here, that is I1. Then multiply by 6, it will give me the Vx. And in this way, our Vx is equal to 1.12 with an angle of negative 84.21 degrees volts, and this is our final value. As long as you know how to use the tables, you will be great in this lecture. Our homework for this, let's say, lecture is these two problems here. Thank you for watching.